You know, every single device you use, from the smartphone in your hand to the laptop on your desk, is powered by a processor. But deep inside that tiny silicone chip, there's a fundamental design choice, a kind of philosophical debate that has shaped literally all of modern computing. Today, we're going to unpack that debate, CISC versus RISC. So, let's just start with a basic question. You might be coding in Python or C++, you might be clicking on icons, but what language does your computer actually speak? I can tell you it's not English, and it's not even just ones and zeros in the way you might think. There's a sort of inner language that the hardware itself is built from the ground up to understand.
And that inner language has a name. It's called the Instruction Set Architecture, or ISA for short. Think of it as the processor's native tongue. Now, how you design that language is a huge, huge decision. And for decades, there have been two major competing schools of thought on the right way to do it. So let's dive into the first one.
All right, first up is the original approach, what's known as CISC. That stands for Complex Instruction Set Computer. And when they first started building processors, this was, the most intuitive way to go about it.
The philosophy here was pretty straightforward. More is more. The whole idea was to make life easier for programmers. How? By creating really powerful, complex instructions that could do a bunch of different steps all at once. You just let the hardware do all the heavy lifting.
Let's look at a classic example from the x86 architecture. That's the kind of CISC processor that powers most desktops and laptops. An instruction might add two numbers, but here's the catch. It's forced to overwrite one of the original numbers with the final answer. This kind of two-in-one operation is a total hallmark of CISC. Yeah, it's powerful, but it bakes a layer of real complexity right into the hardware itself. And that complexity leads to these core traits. You've got single instructions trying to juggle multiple operations. You have this huge menu of different ways to access memory. And the instructions themselves, they can be all different lengths and sizes, which, as you can imagine, makes decoding them a real headache for the processor. The whole focus is on building this incredibly capable but also incredibly complicated piece of hardware.
But then, back in the 1980s, this really counterintuitive idea started what you could only call a revolution. And it was called RISC, which stands for Reduced Instruction Set Computer. The RISC philosophy just completely flipped the script. The new thinking was, less is more. Instead of making the hardware more and more complex, the question was, why not make it, well, almost stupidly simple? Let the processor do only a very small number of very basic, very fast things. All the complicated stuff could then be handled by the software, specifically the compiler, which is the program that translates our human-readable code into this new, much simpler machine language.
And this wasn't just some random ideas someone cooked up. We're talking about a genuine breakthrough from computer science pioneers like John Hennessy and David Patterson. Their work was so foundational, so important, that it earned them the Turing Award, which is basically the Nobel Prize of computing. And you can just see the beauty in its simplicity. Let's look at a modern example from the RISC-V architecture. The instruction add S0, S1, S2 is it's so clean. It takes the values from two places, S1 and S2, adds them together, and puts the result in a totally separate third place, S0. See? Nothing gets overwritten, it does one thing, it does it perfectly, and it does it fast. Any big complex task is just built by combining a whole bunch of these simple, lightning-fast instructions. Okay, so we've met our two contenders. We have the complex, do-it-all approach of CISC on one side, and the simple, one-job-at-a-time approach of RISC on the other. Let's put them head-to-head. I absolutely love this analogy. Think of CISC as a Swiss Army knife. It's got a tool for just about everything, all packed into one device. It's super versatile, sure, but it can be bulky, and sometimes it's slow to find and fold out the exact tool you need. RISC, on the other hand, that's a scalpel. It does one thing and one thing only, but it does it with incredible speed and precision. If you need to do complex surgery, you don't want a corkscrew. You want a series of fast, precise cuts from a dedicated tool. This table really lays out the trade-offs perfectly. With CISC, the instructions are highly complex. With RISC, they're dead simple. Because of that, CISC instructions can be all sorts of different lengths, while every single RISC instruction is the exact same size. And that makes them way easier for the hardware to process quickly. This all leads to a critical difference in execution time. A complex CISC instruction might take multiple clock cycles to finish, but a simple RISC instruction, it's designed to be done in a single cycle. So you see, the complexity has to live somewhere. With CISC, it's baked into the hardware, With RISC, it's shifted to the compiler, which has to be really smart about how it strings all those simple instructions together to get a complex job done.
So if both approaches have their pros and cons, how did this story end? Which philosophy came out on top? Well, in pretty much all of modern computing, there is a clear, undisputed winner.
Yeah, this number is just staggering. Over 99% of all new processors sold today are based on RISC architectures. Now, CISC chips like the x86 family still power most of our desktops and servers, but that's a tiny, tiny fraction of the total volume. The world, it turns out, really does run on RISC.
So why? Why the near total takeover? Well, it boils down to 4 huge reasons. First, and this is the big one, power efficiency. Simpler hardware just uses less electricity. That might not seem like a big deal for a PC plugged into the wall, but it is everything for the smartphone in your pocket. This was the aha moment that truly sparked the mobile revolution. Second, speed. Those simple fixed-length instructions are perfect for a technique called pipelining, where the processor works on multiple instructions at once, like a super-fast assembly line. Third, simpler designs are just plain faster and cheaper to develop and manufacture. And finally, scalability. Because a simple processor core is physically smaller on the silicon chip, it leaves a ton of extra room to add more cores or other specialized hardware.
And that's really the big takeaway. The next time you pick up your phone or you see a news story about some massive new data center, just remember that the engine driving pretty much all of it is based on this wonderfully elegant idea that sometimes the simpler solution really is the most powerful one.
But, technology never ever stands still. As our demand for computing power for things like AI just continues to explode, designers are in this constant juggling act between speed, power, and cost. And that leaves us with one final fascinating question. Could that old idea of complexity ever make a comeback, maybe in a new form that we haven't even imagined yet?